My name is Lyndon Lamborn, and I did 30 years with Boeing, mostly in the helicopter end of things. I used AFGROW, lots on helicopter parts, hub parts, and now I'm in the pipeline industry, trying to convince my fellow engineers in the pipeline industry, kicking and screaming, to adopt more modern fatigue crack growth modeling. And so I've done some work here on circumferential and spiral weld flaws that we have seen and we might see in pipeline service, and so that's some of those results are quite encouraging. So I volunteered to share those results with this group. So hopefully you'll be able to get something out of it. Uh, so first of all, I'll talk about circumferential crack growth. This is very rare in the pipeline industry to have a circumferential crack that grows through fatigue, but we have seen some isolated cases, and so I've applied AFGROW modeling to that. And then a big question among our pipeline operators is spiral welds. Um, we do have these in service, being cycled quite heavily. When I say cycled, that's pressure cycling. The question among industry operators is, are we going to see fatigue problems in the future? And then I'm going to get into some of the details on how we resolve the loads and the stresses to be able to model the growth of these cracks, and also some of the quality control. And we do what we call a proof pressure test. And that leads to surviving flaws that might survive a proof pressure test, which becomes important for us to determine our susceptibility to cracking. So kind of a scattered theme, but hopefully it'll ring some bells and spark some ideas for others here. So I picked here there are 4 cases of circumferential crack growth that we have seen in service. Um, Cases A and B were actual leaks after 21 years in service and 36 years in service. This is uh, time to leak really here in this column. And then case C was a crack that was found just about through wall, didn't really leak, but that was 70 years in service. And then we've modeled those and applied the AFGROW model to it. And here's the predicted time to leak. Now this case B was a very long crack, and not surprising probably to the audience. Sometimes these very long cracks, they don't really act as long as the lab says they are. Uh, there's a characteristic length that really is uh, more defining of its pressure carrying capacity. And so I've modeled those at shorter lengths to get a better correlation, which is a different solution in API 579. API 579 is the kind of our governing fitness for service document for pipelines. This is where we get our stress intensity solutions, which are based on finite element analysis. So I know there's a lot of stuff to take in, but these are the diameter and the wall thickness of the pipes, the defect sizes, and uh, I'll go into case A here to show you what we've done. I've worked very closely with Jim and Alex, so we've developed tabular DADN curves for these pipeline steels. We've had to do some testing to fill in the gaps, but we have arrived at we think are good curve fits for the data we have. This is in girth welds. This is a high heat welding operation, which tends to leave a lot of residual stresses. And so here's a typical residual stress curve that's recommended in our governance documents, API 579. And so we take typically about a year of load cycling, and it's characteristic of the time it's been in service. And then we use that uh, in the model, and then we predict the life. Now the stress intensity solution here that I typically used in this case, it's this solution here. is for an above ground pipe. But most of our pipes are buried. Our onshore pipes are buried in soil. And so the governing longitudinal stress is really governed by Poisson's ratio and not half of hoop. And so we have to correct for that using a zero point 0.6 factor. So if I do this correction, also distance from pump station becomes very important, because this is our measured loads at the discharge of our pump. But as you go downstream away from the pump, of course, those loads attenuate. And so we apply a pressure scaling factor based on distance from pump station. Uh, and again, I know this is a lot to take in, but again, here's my summary here. Very, very good correlation for cases A and B subscript II with a reasonable length cap. AFGROW's predicting life very close to what the actual life was. We'll talk about case C here in a minute. Now, case D, I included case D because what we saw in that one, we saw some growth, and then the crack went dormant. It did not grow. And so we wanted to see if AFGROW would also predict that this would go dormant. And it does predict a life of 6,000 years, which in terms of reality, that is infinite life. And so AFGROW correctly predicts that this crack will not grow in the time horizon we're worried about for pipeline lifetime. So that's why I included case D. Now let's talk about, okay, and of course the question comes up. So it looks like it works for circumferential cracks, but what about spiral welds? Can we predict spiral weld crack growth? And so we'll talk about that here in a minute. Oh, I wanted to give you a feel for that case A circumferential crack that went through wall in 21 years. It was a very, very severe crack, 78% wall thickness deep. And then it took quite a bit of time to grow through wall because the loads are pretty light. And it was a little over 13 miles from pump station. And here's the details that goes into case A. At Enbridge, we take usually a 90-day time slice. So I took a characteristic 90-day time slice, and being lazy, I just duplicated it 4 times in my Spectre Manager to give me a year's worth of load cycling. That makes it easy for me to interpret the results. And then taking into account the scaling factor, converting PSI to KSI, and the Poisson effect gives me a total scaling factor of 0.0048. And then here's your model showing the circumferential crack, pipe diameter, and wall thickness, etc. Again, I was surprised how accurate this was. Yeah. Now, for case C, this was a bit of a head scratcher. AFGROW's predicted a very long life for case C, but yet it went virtually through wall. Well, when we broke open the thing, you might be able to see, hopefully you can see, a very narrow band here of fatigue striations, pretty high cycle fatigue. And then these other portions of the fracture surface were really quite indeterminate as to what was going on. We couldn't really see striations in there. So our thinking here is this is the region of crack growth, was about 40 thousandths worth of depth. And all the other stuff was pertained to weld flaws. Is the best explanation we could. We oftentimes you can't be sure of these things, but we did model this in AFGROW, and I got a slope here of about 5/10 thousandths per year in an inch of growth. And so over 70 years, we'd expect maybe about 36 thousandths worth of growth. And of course, that does roughly match our observation here for this band of high striation. So we think that AFGROW is actually working correctly here, and we just have kind of an unusual interaction between these weld flaws that caused it to go near through, or it actually went through wall. Okay, shifting gears. See how I'm doing in time. Got reasonable pace here. Switching gears now to spiral welds. Of course, there's no stress intensity solution for spiral welds currently published. So the thinking is we'll just use this the solution for a longitudinally oriented crack, and then we'll suppress the bulging factor, and we'll resolve the stresses to those normal to the spiral weld. So that's this equation here. And time we do that and we suppress the bulging factor, we get a total reduction factor shown here in the solid black line. Um, then I did this is for the pressure vessel solution. But anyway, based on how uh, your spiral weld angle, how off axis it is. So all the way from 0 degrees to 90 degrees. Most of our spiral welds are helical welds. Now, we're talking about a helical weld. That's like the the cardboard on a roll of toilet paper. That's how the weld is oriented. Uh, and usually they're around between 30 and 60 degrees. Depends on the width of uh, the pipe scalp or the sheet that you're rolling at the mill, and the diameter of the pipe. That determines the helical weld angle. So these are the different situations we might encounter for spiral welds: above ground, buried close to a bend, and buried a ways away from a bend, and how we would theoretically resolve the pressure loading into stresses normal to the spiral weld. We're neglecting shear stresses. I think I've just described everything else on there. We're assuming that mode one is going to dominate here. So we really don't have any incidents in our pipeline industry yet on spiral weld fatigue growth, and so, but we do have a test. So I'll show some. We got some burst test data, but I'll show that in a few minutes. But in terms of fatigue test results, we really only have this one test. Here's the specific values. When it is a 30-inch pipe, it's X70 grade, which means 70 KSI yield strength minimum. And we encountered a leak at 44,000 and change cycles here in the spiral weld, which was not anticipated. And then we broke it open and we saw it was about 45% deep and 1 inch long. It's a very small flaw. This would be a flaw that potentially the quality control at the mill could miss. And in fact, they did miss it. And so we put this into AFGROW, and I had to do all these manipulations. First of all, I had to take into account, as I showed on the previous slide, suppress part of the bulging factor. This is about a 51-degree weld angle. So I'm in this region here for suppressing that and resolving the stresses to mode one along the spiral weld. And I threw all into AFGROW, the scaling factor, etc., using this model. Also, by the way, we use a projected length, so onto to a longitudinal plane, with very, very low hopes that I would get any kind of accuracy. And on the first try, assuming that it went through all at 95% depth, the cycles to fail was 42,200 cycles. This is the closest. This is the first time in my whole career I've matched anything so closely on the first try. And if I assume this at 99% through wall, I get 44,100 cycles to leak. So this is unheard of correlation, but again, it's only one data point, so I can't put much stock in it. But this was uh, a huge success, at least for a first try. So the question might come up in your mind is, if the principal stress is the hoop stress, which it is, why wouldn't this crack turn and go to grow in a longitudinal plane, which should be normal to the hoop stress? And that's what I would expect. But you got to keep in mind, this is a desal weld, a double submerged arc weld, and this is the shape of the weld. And so what you got here is you got a toe crack that starts here, and in order for it to grow into a longitudinal plane normal to the hoop stress, it has to overcome this increased thickness. You got quite a bit of increase in thickness, at least at 25%. And of course, what we saw in the test is it did not. It did not turn and go normal to the hoop stress. It stayed right along the weld. Of course, that could be somewhat due to metallurgical properties as well, because we do have a heat affected zone here uh, from these weld beads. And so that was a very interesting result. And it could be that we'll find, even if we were to apply other kinds of crack growth, natural crack growth modeling to these things with these weld caps, that these cracks will grow through wall before they turn and go into a longitudinal plane. But anyway, I won't go into that anymore. Finally, as we wrap this up, the thing we've seen in our axial cracks is we don't really see them past the 20-mile marker, because really what happens is we do a proof load test, and any cracks that are relatively big, they fail. They fail during the proof pressure test, and so we're left with only cracks. And this is a concept only thing. We wind up with only cracks that are in this zone here, and they would perhaps be susceptible to grow in the first 20 miles from pump station. These features that are higher stress intensity, they're all eliminated. So what does that, can we take some learning from this and apply it to spiral weld? And so, but in order to do that, we needed to get a burst model, which I leveraged some prior work done by both Enbridge and Seifer, a consultant, and use that model with pretty good correlation to actual burst pressure. By the way, oh, I'm sorry, this is kind of scattered, but what we wind up with is for spiral welds, these flaws have to be pretty big. To the ones that survive the pressure test, and these would be features that most likely get caught in quality control. Now, I plotted, just for my own sanity, I plotted these cases from another paper. They're not related to the first cases C, B, and H, which are X70. And this is a paper that Jim and I published a while back. We took these cases, I took these and see, would these survive the hydrostatic test? And yes, they do, because they're below the line. They would survive the proof pressure test, and obviously they were susceptible to growth because they did grow in service to the point where they leaked. And so, in conclusion, we really feel good about the performance of AFGROW on circumferential crack. The assumptions we're making about the Poisson effect governing things appears to be appropriate. The pressure scaling we've applied appears to be appropriate, which of course we do have some corroborating evidence of that. And we did confidently predict a dormancy case for comparison. Now for spiral weld, we did have a great success predicting the test case exactly. Now the cracks did not turn and reorient in a longitudinal plane as we expected. So this is something that we'll be sensitive to as we go forward, as we research this more. And surviving flaws may become very important for us to help manage spiral weld cracking. We do have a lot of ongoing and future work. There's a project that's co-sponsored by the Government of Canada with the University of Alberta that we're working on with some graduate students, and a related PRCI project, that's the Pipeline Research Council International. And we also have other related work going on with the Research Council to make sure that we're being safe in as we cycle these helically welded pipelines in the future.